We want to look at this question related to the Poisson approximation to the binomial distribution. This is exercise 4.59, which says that the corporation has 250 personal computers. The probability that any one of them will require repair in a given week is 0.01. Find the probability that fewer than 4 of the personal computers will require repair in a particular week. And they're asking us to use the Poisson approximation to the binomial distribution. So the question explicitly asks us to use Poisson. Okay, so let's first define a random variable. So let the random variable x. So what are we interested in? We're interested in number of personal computers that will require repair in a particular week, right? So that's what we're interested in. So let's just highlight what we are interested in, and we'll define a random variable based on the personal computers that will require repair in a particular week. This is what we're interested in. This is how we'll define a random variable x, right? We want to find, so we'll define a random variable in line with this. So the random variable x denote the number of computers that will require repair, right? In a particular week that will require repair. Right, so if you notice over here, the next is a binomial random variable where n is basically 250, because you can see over here, this is n, which is 250 over here. And the probability of success is given to us as 0.01, right? So this is x, and we know where a binomial random variable takes values starting from 0, 1, 2, so on till the number of till n, right? Because these are the maximum number of successes that you can have. So let's just okay, let's just do this. So this is our p, which is 0.01 over here, right? Right, so this is this, and basically over here, note P is like this because note, remember success is defined, a binomial random variable is defined as number of successes in any dependent trials, right? And success is defined in terms of whatever we're looking for. Success here is defined as, so success here is defined as computer requires repair. Computer, that is what we've defined and requires repair. Now, how do we know this is binomial? You have a finite number of computers, and every computer obviously requiring repair will be independent of the other, and you have a constant probability of a computer requiring repair, right? So constant probability of success. So this is fine. I want to use the Poisson approximation. Right, so now the idea is that the question has told us that to use Poisson. We want to use the Poisson approximation. The question is explicitly asked us to do that. So we want to use the Poisson approximation to solve this binomial question. Now, when we use Poisson approximation, we know Poisson random variable has one parameter lambda, which represents its mean value and its variance, and we need to know the parameter to find any probabilities concerning this Poisson random variable. When we use the Poisson approximation to binomial, then the parameter lambda, right? Because Poisson has the parameter lambda, which you need to first find before you can apply Poisson, right? So the lambda that you use when you're using a Poisson random variable to approximate a binomial random variable is NP, right? NP is just the mean value of the binomial random variable. So that is what you use as your parameter for a Poisson random variable, right? Lambda, which represents its mean and variance. So now n over here is 250 and p over here is 0.01. So lambda is just 2.1, right? So we're saying x is a Poisson with parameter lambda because it has one parameter. Binomial has two parameters n and p, which you need to find any probability regarding the binomial random variable. Poisson has one parameter lambda. So when you're using the Poisson approximation to binomial, you first need to make sure you find this lambda. Only then you can find any probability for this Poisson random variable. And when you're doing a Poisson approximation to binomial, this parameter lambda is just np. It's just the mean of the binomial random variable. Lambda is 2. And this is approximately, right? Because we know x in x we know follows what? We know x actually follows a binomial distribution, but we're approximating it using a Poisson distribution. So we need to write approximately here because its exact distribution is binomial. We're just using an approximation here. And under this approximation, we know x is taking values 0, 1, 2, and so on, right? Binomial random variable only takes values till n, but a Poisson random variable takes all non-negative integer values, all non-negative integer values. Non-negative is in this, why? Because it can be positive integer values or 0 as well. All non-negative integer values, right? So let's actually solve this. Now before that, let's just clear this up and let's just write over here. X is Poisson, lambda is 2.5. Again, it's important to write approximately because the actual distribution is where x is 0, 1, and so on and on, right? It's always important to keep in mind the values a random variable takes. Now I want to find the probability that fewer than 4, right? So I want to find the probability x is less than 4, right? Fewer than 4 means less than 4. Now, whenever you want to find any probability for a discrete random variable using its PMF, which you can just sum up the PMF over those values, right? So that's what's important to keep in mind the values it takes. So if I just write a couple of more values here, 3, 4, and 5, and so on, right? So remember, whenever you want to find the probability a discrete random variable using its PMF, we just sum up the PMF for those values, right? So this means to find the probability x is less than 4, I'll sum up the PMF for all those values are less than 4, which is 0, 1, 2, and 3. This is why it's important to keep in mind the values the discrete random variable takes, so you can sum up the PMF for the relevant values, right? So how this could be done? This could be simply done as probability x is. So this is like x can take a value 0, x can take value 1, x can take 2, x can take 3, right? So the way we would have done this is probability x less than 4 is just this, you just sum of the PMF over all those values. So this is probability x is 0 plus probability x is 1 plus probability x is 2 plus probability x is 3. Let's just try to understand the logic behind why we sum it up. Why the summing up thing works. The probability x is less than 4 means the probability x is 0 or probability x is 1 or x is 2 or x is 3, right? This is what x could potentially be if it's less than 4. Now over here, something to keep in mind is that or means union, right? So I can rewrite this as probability x is 0, union x is 1, union x is 2, union x is 3. And we now random variable taking on different individual values, like over there x is 0, x is 1, x is 2, x is 3 are mutually exclusive events, right? Because when you perform a random experiment, you get exactly one outcome. So you get only one value, the random variable corresponding to this outcome. You can't have the random variable taking on two different individual values when you perform the experiment, right? So these are mutually exclusive events. And we know, okay, probability of union of mutually exclusive events is the sum of the individual probabilities. So I can write this like this. So this is why the summing up thing works. The logic behind this is these two steps, right? The probability exists. So this is just the logic, although we know, okay, we could have done that, right? Since mutually exclusive, right? Right, so just keep in mind, we know, okay, whenever we want to find the probability of a discrete random variable using its PMF, we can just sum up the PMF over all those values. This is what we've exactly done here. We have summed up our PMF over all those values, x is less than 4, probability x is 0, plus probability x is 1, plus probability x is 2, plus probability x is 3. But we've also understood what the logic behind this summing up is in these two steps. So just keep in mind the values it takes is very important, because for you to know what does x is less than 4 curtail, which values does it mean x can take, you need to keep in mind what values this random variable can take. And we know Poisson random variable, we're using a Poisson approximation, and a Poisson random variable takes non-negative integer values, right? So let's actually find these probabilities. So for that, let's recall what the PMF is. Let's just erase this much, have more space. So now let's recall. PMF of Poisson random variable is PMF of Poisson random variable. So this is not a Poisson random variable, this is an approximation, but because we're approximating using Poisson, we have to use its PMF. K is E minus lambda power K by K factorial. So in this case, lambda is 2.5, right? That's why we have to find lambda, because we said this is a parameter for the Poisson random variable, and you need this parameter to answer any probability question regarding it. And now you can see once we plug in lambda's value here, then we can find the probability x is equal to any value. Oh, sorry, x is equal to any value k, right? So lambda is 2.5, so it's minus lambda 2.5 power k by k factorial. Now let's actually use this now PMF that we have. So probability x is 0. Instead of k, you just plug in 0 here. So this will just become e minus 2.5. 2.5 power 0 divided by 0 factorial. 0 factorial is 1, so this is not an issue. Probability x is 1. Instead of k, just plug in 1 here. E minus 2.5 2.51 divided by 1 factorial. Now probability x is 2. Instead of k, just plug in 2 here. So this becomes e minus 2.5, 2.5 power 2 divided by 2 factorial. And similarly, probability x is 3. Instead of k, just plug in 3 here. E minus 2.5, right? And then this becomes 2.5 power 3 divided by 3 factorial. And you can solve this to get the final answer would be 0.76, right? And this way we can use a Poisson approximation to a binomial distribution. Just keep in mind, to use a Poisson approximation, you need this parameter lambda, because once you have this lambda over here, like you can see, you can find any probability concerning it. And this parameter lambda is just equal to the mean of the binomial random variable which you want to use the Poisson approximation on, which is NP.